and welcome class to another lecture here in chapter 14, where today we will be discussing the dependence of reaction rates on the variable of temperature. So in part 1 we talked about a number of variables that the reaction rate is dependent on due to the rates dependent or dependence on the number of effective collisions that can be made, right? And the number of effective collisions was proportional to the overall reaction rate. In part 2, we talked about how the concentration can increase the number of effective collisions and looked at a couple of different ways that we can explicitly calculate the rate of a reaction through the concentration. Today we're going to be focusing then on the temperature aspect. So we're going to be assuming in this situation now that concentrations are held somewhat constant so we can get an idea for how the temperature plays into the reaction rate. All right, so how we find the dependence of the rate on temperature is through what is known as the Arrhenius Equation, which we can see below. The Arrhenius Equation was first written by Funday Arrhenius, who lived from 1859 to 1927, another phenomenal scientist. He won the Nobel Prize for his discovery that ions in solution conduct electricity. So something that we take for granted almost today, this knowledge that ions in solution conduct electricity, was first discovered by Funday Arrhenius like barely even over 100 years ago. All right, so not only did he dabble though with ionic equations, he dabbled with acids and bases and also with reaction rates. So he was studying the kinetics of these particular types of reactions in aqueous conditions. He found what the temperature dependence of the rate was through, or like in conjunction with a couple of other variables through this equation down below, where he was the one who defined explicitly what the rate constant K is equal to. As we've already seen in part 2, a greater K would signify a faster reaction because the place of K in calculating the rate is through our generic rate law expression, where rate is equal to K times the concentration of one of our reactants to the M times any of our other reactants to the N, etc. Now we have already again focused on this concentration dependence. What we're looking at here is what K is and how K therefore is going to impact the rate. As K increases, we would expect the rate to increase, and as K decreases, we would expect the rate to decrease. Now K is equal to this variable A times the base of E raised up to the negative activation energy divided by gas constant R divided also by T. So in other words, K is directly proportional to this variable capital A. Now this A is not related to activation necessarily, but it is a variable known as the collision factor. So it is kind of related to activation, just not necessarily in the energetic sense. So if you remember back when we first introduced collision theory, we also, in addition to energy, stated that we needed proper orientation of our molecules coming together in order for some type of chemical reaction to occur. How we take this explicitly into account, along with a couple of other statistical measurements, is through the variable of the collision factor, capital A. Now the rate constant K is also inversely proportional to our activation energy. So the activation energy, again, is the amount of energy needed to get your reaction started. It's the toll that you need to pay to get your reaction moving in the first place. And every cycle through the reaction, you need to be paying this toll. So the greater the activation energy, the lower your K. So greater activation energy, lower the K. And as we also know based off of the rate law expression equation, the lower the K, the lower the rate. So we can see here explicitly how the activation energy relates to the rate of the reaction. The greater the activation energy, the slower your reaction is going to go. Now we can also think of this more qualitatively, that every time your reactants turn into products, you're going to have to be paying this toll. And the higher this peak, the higher the activation energy, the more time needs to be spent to put this energy in, And of course, the more time that goes into the reaction cycle, the slower your rate as well. All right, R, again, is a constant. This is the gas constant. And since we can see that we are working with energy units here due to the activation energy being present in this numerator, this tells us that we are working with the 8.314 joules per mole Kelvin version of the gas constant. And last but not least, we have temperature T. So our rate constant explicitly demonstrates how temperature is going to directly impact the reaction rate. And on day one, we already talked about how, greater the temperature, the more molecular motion you have, which means the greater the chance of an effective collision. Well, here we can see explicitly how we can incorporate temperature into calculating exactly how fast the rate will be. Since the temperature here is in the denominator of this negative exponent, the greater the temperature, the greater the K is going to be. All right, so all in all, our rate constant K is directly proportional to the collision factor, it is inversely proportional to the activation energy, and it is directly proportional on temperature. So each of these factors, each of these variables are related to K in the way that we would expect them to be directly related or inversely related to the rate. All right, so how did Svante Arrhenius find this experimentally? He played around with some variables. We're not going to get into the details exactly of how he derived this equation, but we will be talking about a couple of other forms of this equation that are more useful in a modern setting to be able to find how, let's say, activation energy and temperature specifically relate to your overall reaction rate. There are two different versions of the Arrhenius equation that we're going to be talking about today. The first, which we can see labeled here, is version 1, is a straight line form, a linear form of the Arrhenius equation. How it's found is by taking the natural log of both sides of the previous equation. So if we go back to this previous slide, and clean it up a little bit, in order to derive version 1 of the Arrhenius equation on the next slide, all we have to do is take the natural log of K and the natural log of A times E, all raised to the negative EA divided by RT. Well, natural log of K we're going to leave as a natural log of K. Natural log of A times the the natural log of A times E raised to the exponent here is going to be equal to the natural log of A plus the natural log of everything, or E times everything that's in the exponent, our negative EA, divided by RT. Big parenthesis here. And so mathematically, the natural log of A is going to remain as natural log of A, since A is just a constant value here. The E, though, is going to cancel out with this natural log, and everything from the exponent is going to drop down in front. So if we move back to the next slide again, we can see exactly that's the equation that we have here. Natural log of K is present, natural log of A is present. We've just moved what was in the exponent from being behind the natural log of A to being in front of it in order to match this y is equal to mx plus b format. So our y-intercept is going to be equal to the natural log of K in a graph like we can see here on the right. The slope m is going to be equal to our negative activation energy divided by constant r. Our variable with which we can measure pretty easily in lab is going to be temperature. Therefore, we will say 1 over our temperature is going to be our x. And we will add to this our y-intercept, the natural log of A. So our dependent variable is equal to natural log of K. X is equal to 1 over t. This is our independent variable. Now, the reason why we love having these types of straight lines is because it helps us to be able to map this, the data points that we can measure and gather some information about our experiment a little bit easier. So as we can see on the right, what we have done here is taken a reaction at a series of different temperature points, which we can see were also measured in inverse of Kelvin, since we're looking at a variable of the inverse of temperature. And we've also, at each of these temperatures, found what our rate constant is, our K. Now we can find the rate constant K experimentally using the rate law expression. So the same method that we learned in part 2, our previous lecture, to find K, can be useful here. The difference is that we're going to be keeping constant initial concentrations and varying temperature instead. So we will end up finding different rate constants K so long as we're varying the temperature, even if we're holding the same initial concentrations. And so if we take the natural log of each of those rate constant K's that we found, plot them versus our 1/t's, we will find this straight line relationship between these data points. So as we've seen now multiple times in lab, you fit a line of best fit through this scatter plot. This will give you a y is equal to mx plus b equation, and now you have the means to find your collision factor A, since this is equal to your y-intercept here. Whatever the data point is here, it looks like it's maybe around 27 point, let's say 4-ish, just by looking at this graph for the particular reaction that was being observed here. This will be equal to your natural log of A. So if you actually want to find your A, you're gonna have to raise both of these sides up into the exponent of E. And so your collision factor A in this case will be equal to E raised to the power of 27.4. This may be a number that your calculator can crunch. This may not be, all depending on the strength of your calculator. And if your calculator is not strong enough, providing an answer like E raised to the 27.4 is a perfectly acceptable answer. The other piece of information provided is the slope, where again, your slope is going to be a measure of like rise over run. It's how curvy, not curvy, but like how steep this line is. And so your slope, m, from your y equals mx plus b, is going to end up being equal to some number, and this number is equal to your negative activation energy divided by r. So if you know the value of your slope, you can rearrange to solve for the activation energy pretty easily. The second version of the Arrhenius equation is based off of version 1, but it's just a 2 measured points version instead of the full comprehensive line version. So here we can see that by comparing 2 different data points, the natural log of K1 divided by K2, so if we're like taking the proportion of 2 of our rate constants, this is going to be equal to the positive activation energy divided by R times 1/T2 minus 1/T1. So if we only have, let's say, 1 data point and we're curious about like the rate constant at a different temperature, or at what temperature a certain rate constant is found, or even if we have 2 data points and we're trying to find like activation energy, any of those combinations, this version 2 of the Arrhenius equation is going to be a little bit more useful for us. Not only is it going to be more useful in the sense that we don't need a whole series of data points to figure things out, but we can also see that the 2 measured point version does not include the collision factor A. This is actually pretty nice for us because the collision factor A is a very complicated variable that is dependent on a lot of sub-factors that are difficult to keep track of. Again, things like the orientation of your molecule. So it can be a little bit easier to just use the 2-pointed version when we can get away with it. Therefore, we don't actually have to worry about what our collision factor is in the reaction. So this brings us then to actually utilizing the Arrhenius equation, right? So we've seen all of the variables that our rate constant K is dependent on through the Arrhenius equation. So let's say the rate constant of a particular reaction, we don't need to know exactly what it is, at 300 Kelvin equals 6.5 times 10 to the 7 inverse meters times inverse seconds, where this is synonymous with writing 1/molarity times second. I think I might have said meters. If I said meters, I meant molarity. And at 313 Kelvin, our rate constant is equal to 7.5 times 10 to the 7 inverse molarity inverse second. So our question is, what is the activation energy of this reaction in joules per mole? So we can use the 2-point version of the Arrhenius equation to determine what this is, and I'm going to let you guys crunch through this, crunch through these numbers and figure out what the activation energy is equal to. All right, let's write out our equation for the Arrhenius equation so we can rearrange and solve for our activation energy. So the version that we need is the 2-point version, again, since we're given 2 different rate constants as well as 2 different temperatures. So we're going to take the natural log of K1 is divided by K2 equal to activation energy divided by R times 1 over T2 minus 1 over T1. Now from here on out, it doesn't really matter which data point you insert exactly for 1 versus 2, just so long as the corresponding rate constant and temperature get, plugged into the correct corresponding slots. So I'm going to pick the data point that was listed first to represent our first data point, just to make it simple and consistent. So the natural log of 6.5 times 10 to the 7 inverse molarity, inverse seconds, divided by the second data point, the 7.5 times 10 to the 7 inverse molarity, inverse seconds, is going to be equal to our activation energy, which we do not know, divided by our constant R. And this R again is going to be equal to the 8.314 joules per mole Kelvin version of our gas law constant. And we can see that this is going to really nicely work together to give us an activation energy in joules per mole. Since the quotient here, this divisible, is going to be multiplied by our temperatures, the inverse Kelvin should cancel out, giving us only joules per mole left over. All right, so since T2 is what gets inserted first, we're going to insert the temperature that corresponds to the 7.5 times 10 to the 7 rate constant. This is going to be our 313 Kelvin, and we will subtract out then our T1, which is going to be 303 Kelvin. All right, so from here, it's just a matter of algebraically rearranging your equation. We have something on the left-hand side that can be crunched pretty easily. We're then going to multiply up our 8.314 joules per mole, and we will divide down the 1 over 313 minus 1 over 303. It's going to be very important in this type of problem, again, to make sure that your parentheses are keeping what needs to be divided or subtracted together, so that way you don't accidentally end up with something in the numerator when it should be in the denominator. But if your calculations work out correctly, so I'm going to leave that as a little algebraic exercise for you, your answer should come out to be equal to 1.13 times 10 to the 4 joules per mole. So we can see that the activation energy here is a positive number. This makes sense since we know, again, if we're keeping track of energy in versus energy out, energy, or the activation energy, is an energy in requirement, meaning that it should be a positive value. If you ever get a negative activation energy, what this would symbolically tell you is that the reaction actually needs to release energy to get started, which doesn't really make much sense when your activation energy is supposed to be an energy requirement. So that can be a little way to keep track of whether or not your algebra is making sense. Your activation energy should end up being a positive value. All right, in addition, the magnitude here makes sense. We're working with the joule, not the kilojoule, so our answer would be expected to be somewhere in the hundreds, if not thousands, of joules. And here we can see that we're working with around 10,000 joules of required energy to get this particular reaction started. And believe it or not, that's it for this section. So the reaction rate, as is dependent on temperature, is fairly straightforward. It just involves the introduction of one new equation, the Arrhenius equation. The Arrhenius equation also then conveniently helps to incorporate our activation energy, again, as well as our collision factor, into how we can find the dependence of our reaction rate through K. So if you would like some additional example problems working with the Arrhenius equation, I have some recommendations here. But as always, if you have any questions, please do not hesitate to reach out. If you have homework, please double check and do your homework. And until next time, class is dismissed.